Hi everybody, this is the last lecture of the semester. So congratulations on making it this far, especially during distance learning. Let's get down to it so you guys can work through your homework. Couple of things to think about with reciprocals because we're going to be graphing cosecant and secant today, and they are reciprocals of sine and cosine. We'll also be graphing cotangent. Just kind of things to think about or keep in mind as we're plotting the points for these reciprocal curves. So let's think about it. The reciprocal of a positive number, still positive, which means the reciprocal of a negative number, still negative. Doesn't change the signs. The reciprocal of 1 is just 1. The reciprocal of negative 1 is still negative 1. But the reciprocal of 0 is undefined. Remember that we can't divide by 0. So 0 has no reciprocal, it's undefined there. That's going to be really important because we're going to see asymptotes in our cosecant, secant, and cotangent curves, as well as tangent. All right, next up, let's call all numbers with an absolute value less than 1 little. So we're talking about like small fractions. And all numbers with an absolute value bigger than 1 are big. Okay, so we've got little numbers less than 1, big numbers greater than 1, no negatives. The reciprocal of a little number is then big, right? If I take 1 over 4, the reciprocal is 4. 1 over 2, the reciprocal is 2. The reciprocal of a big number then is little. The reciprocal of 4 is 1/4. So big number's reciprocal is little, and a little number's reciprocal is big. It's also going to help us when we go to sketch the graphs of cosecant and secant. We think about the values of sine and cosine at those places. As x approaches 0, 1 over x is going to get bigger and bigger and bigger and bigger. So our function is going to approach infinity. And as x approaches infinity, 1 over x, well, that's where it gets really, really small. So if you think about the graph of 1 over x, as x goes to positive or negative infinity, it gets closer and closer to the x-axis, but never hits it because we've got an asymptote there. But it does approach 0. Right? So as we get to bigger and bigger, its reciprocal gets smaller and smaller. As we get smaller and smaller, going back to 0, we get bigger and bigger on the reciprocal side. And that'll inform us about how those curves are going to look when we sketch cosecant and secant today. Okay, so today I am on page 32 of your student note packet, the top graphs of reciprocal functions. What graphs I don't finish for this whole entire handout, that goes all the way through page 35. You guys are then going to do on your own for homework, and then you're going to scan everything in. I do want to make a note that I'm not assigning additional bookwork like I would in regular years. You've got enough to do in addition to this lecture. But it is really important that you guys can identify graphs of cosecant, secant, tangent, and cotangent curves. So please be really careful and thoughtful as you guys are finishing up the rest of these graphs. Check your work using a graphing calculator or Desmos. Make sure that you've got the rest of the graphs that I don't cover with you correct, so you guys are good to go for the test. So the first one we're going to start with is at the top of page 32. We're going to graph sine, and then we'll graph its reciprocal, which is cosecant. So our sine curve, I've got everything labeled along the x-axis for you guys already. We're going to really quickly sketch in the sine, and then we'll more closely focus on cosecant here. So we've got our standard sine curve. Remember that the standard sine curve has a period that is 2 pi, standard period, 2 pi, which means that the sub-interval length is 2 pi divided by 4, or pi over 2. So every pi over 2, we're going to be graphing a new key point for sine. Now, our amplitude here is 1, so our min is negative 1, our max is positive 1, and we're going to sit along the x-axis as far as the sinusoidal axis goes. We're not shifting up or down here. So very simple sine curve. Remember that sine starts on the axis, and then every pi over 2, we're going with the order of key points. So 3 pi over 2, we're down at negative 1. Then we end up back on the sinusoidal axis. And I'm just going to make sure that I fill this whole entire graph up. It's already labeled for you guys, so please do the same for all these curves. Go all the way left and right of what I've given you. And then I'm just going to sketch in the curve here. So this is our sine curve. Okay, and I've got my sine curve graphed, and I'm going to do this in different colors so we can actually see the difference between sine and cosecant. Now, I always think that it's really easy once I've got the key points for sine or cosine graphed. In order to graph cosecant and secant, you can always sketch the curve in, but if I'm just asking you to graph secant or cosecant, you don't need to graph sine or cosine with it. All right, so cosecant I'm going to do in purple. We're going to think about cosecant, though, as the reciprocal of 1 over sine. If we go back to our reciprocal discussion on the last slide, we can kind of start seeing where a cosecant curve is going to be. First thing I'm going to think about is where cosecant is undefined. Cosecant's undefined when sine is 0, right? When sine is 0, cosecant is undefined because we can't divide by 0. So everywhere our sine curve is 0, our cosecant curve is going to have an asymptote. We can see that really easily, really quickly, because we've got all the key points of sine already graphed. Every single place where sine is sitting on the x-axis, we're going to have an asymptote for cosecant. Now the asymptote belongs to cosecant, has nothing to do with our sine curve. Sine and cosine don't have asymptotes, which is why these are in purple. So I'm keeping the graph separate with colors. Okay, so we've got our asymptotes graphed. So now let's think about where cosecant is going to get really small and where it's going to get really big. And then once you've got that pattern down, it's pretty simple to go from there. Okay, I'm going to start in this section here. Okay, so focus right there where I'll be drawing. And we think about this, right? We've got this point here. 1, and cosecant is the reciprocal of sine. So at 1, the reciprocal of 1 is just 1. So we have that point that cosecant and sine share. Same thing for the -1 value as well. Right? So cosecant is defined at all the places where sine has a minimum or a maximum. Those are the points that they share in common. Right? So I'm going to go over those points with purple. All right, still focusing on this section of the graph. Let's think about where the rest of this curve is going to go. Now, in this section, right, if I'm going this direction, sine is becoming smaller and smaller, right? We are approaching 0. Sine is approaching 0. It's going smaller and smaller as we go that direction. Also, if we go to the right, we're approaching 0 in both directions from that maximum. So think back to our discussion about reciprocals. As x approaches 0, the reciprocal 1 over x is going to approach infinity. As our sine curve gets smaller and smaller, our cosecant curve is going to get bigger and bigger. Because they're reciprocals of one another, that's how the math is going to work out there. So the way that we're going to do that is we're just going to represent the cosecant curve getting bigger and bigger as sine gets smaller and smaller. All right, the same thing happens on the negative side of things, but it's going to go more negative because the reciprocal of a negative number is always negative. All right, but all we need to know really is that from those minimum and maximum points, our cosecant curves are going to go up or down and follow the asymptotes to positive or negative infinity. All right, so what's in purple, including the asymptotes, is cosecant. Always have to graph the asymptotes if you want full credit there. What you didn't need to graph, if I didn't ask you to graph sine, is that green curve that goes in between. Okay, so let's work through this second example a little bit faster then. We've got the graph of the sine of 2x. So the first thing we need to do is we need to find the period of this. So remember that the period is always 2 pi divided by the frequency. In this case, the frequency is 2. So our period here is pi, which means that the sub-interval length is going to be pi over 4 this time. So we're going to be counting every pi over 4 instead of every pi over 2 for our key points. We're still not shifting up or down. There's no phase shift, so we're not moving left or right, which means we're starting at 0. There's no amplitude change. So I'm just going to sketch in the points for sine here, but I'm going to be counting every pi over 4 instead of every pi over 2. All All right, sine always starts on the sinusoidal axis. In this case, it is the x-axis. And then I am going to go every pi over 4 as a key point here. So we're going to go up, max, axis, min, axis, max, axis, min, axis, max, axis. And then I'm just going to go backwards as well. So every 2 tick marks along the x-axis is going to place a new key point. And then I'm just following the order of key points for positive sign. I'm going to get those negative points graphed as well. All right, so there's my cosine curve. All right, connected the dots, smooth continuous curve there for sine. So let's graph cosecant. So because the frequencies are the same, right, then this is the reciprocal of 1 over the sine of 2x. So I can use all of the key points from the sine of 2x in order to determine the points for cosecant. So we're going to follow the same kind of logic here. Everywhere our sine of 2x curve was 0, we're going to have an asymptote for cosecant. So I need to include all of those like this. Okay, got all my asymptotes. And then, again, we're just going to sketch in the rest of the curve for cosecant using the values of sine and of sine at its minimums and its maximums. So please hit those points at the mins and max of sine. If you miss those, you'll lose points on your cosecant curves on the test. And we're just going to follow the asymptotes, but they're really just a sketch other than hitting 1 or negative 1. And then the only thing that represents that cosecant curve is what's in purple. Remember that that green curve is the sine of 2x. That has nothing to do with the cosecant curve. Just helps us get those points there. So you guys are going to try the last one there, the sine of 1/2 and the cosecant of 1/2. There's just a frequency change that will change how many curves you see. And then you're going to do the same thing for cosine. So graph the cosine curves, figure out where those asymptotes are, and then sketch in the curves that represent secant on page 33. Use Desmos or a graphing calculator to check your cosine and secant curves, but we're going to move on to tangent, and then you guys are going to try cotan on your own. Okay, in order to graph tangent and cotangent graphs, we're going to think about where cotangent and tangent equal 0, where they equal 1, where they equal -1, and where those functions are undefined. We're going to plot those critical points and then make sure that the asymptotes are represented. Always have to graph the asymptotes if you want full credit. And then we'll sketch the rest of the curves there. So if we think about tangent in terms of y over x from the unit circle, okay, tangent is 0 only when y is 0, right? If x is 0, we're undefined. So when y is equal to 0, our tangent value is 0. So on the unit circle, where do we see y is equal to 0? Y is equal to 0 at 0 radians and at pi radians, right? Everywhere x is 1 or -1. Where is tangent equal to 1? Well, tangent's equal to 1 when y and x are the same. When you have a number being divided by itself, it's always 1. So on the unit circle, where is y equal to x in those ordered pairs? Well, that's at pi over 4, and then also at 5 pi over 4 in the third quadrant. Okay, we can see that the spacing here is 180 degrees or pi radians always. Okay, that's where you get the period of tangent. Okay, where is tangent -1? Well, tangent's -1 if y is equal to -x. They are the same value, but one is positive and the other is negative. So where does that occur? Well, that occurs in the second quadrant at 3 pi over 4. In that case, the x value is negative, but the y value is positive. And then also at 7 pi over 4, where the x value is positive, but the y value is negative. Again, the spacing here is pi radians, or 180 degrees. That comes from the period of tangent. And then lastly, where is tangent undefined? Well, tangent's undefined when x is equal to 0. So where do we see x, the x coordinate equal to 0 on the unit circle? That happens at pi over 2, and that happens at 3 pi over 2, where y is positive 1 or negative 1. So at those places, we're going to see some key points for tangent. And if we can remember the order of key points for tangent, then it becomes really easy to graph tangent. All right, so I'm going to make a reminder here that tangent is just the y values of our unit circle over the x values. And let's just kind of start, see if we can figure out a key point order here for tangent, and then it'll become a little bit easier as we go through the rest. Now remember that the period of tangent is pi radians. Okay, the standard period for tangent is pi. That's where we see that in the periodic properties. And so the sub-interval length is pi over 4 for tangent. So every pi over 4 radians, we're going to have a key point. It's very similar to how we graph sine and cosine. The order of key points is just going to be a little bit different. Okay, so let's just plot some points and then go from there. At 0 degrees, or 0 radians here, remember at 0, that's where the y value is 0 on the unit circle, the x value is 1. So at 0 radians, tangent is 0. And then every pi over 4, so pi over 4, that's where x and y are equal to one another. That's where tangent is positive 1. And then another pi over 4 at pi over 2, so pi over 2, that's where x is 0. We have something undefined. Okay, so pi over 2, tangent is undefined. All right, so we've gotten 0, 1, asymptote. Another pi over 4 gets us to 3 pi over 4, and that's where x and y are equal to one another, but one is positive, the other is negative. So at 3 pi over 4, we're at negative 1. And then at pi, we're back at 0. And then 5 pi over 4, that's in the third quadrant. That's where x and y are equal to one another again. 3 pi over 2, x is 0, so that's going to be another asymptote. So hopefully we start to see an order here. 0, 1, asymptote, negative 1, 0, 1, asymptote, which means we're going to be at negative 1, 0, 1, asymptote. It's going to be our order of key points for tangent. If you can remember that, then it makes it a little bit faster to graph, but you can always plug in points from the unit circle as well. All right, so going backwards, at 0, we were at 0, so going backwards, we need to be at negative 1, and then another pi over 4 in that direction is going to give us an asymptote. Right, then we're going to be at 1 again, back to 0, back to negative 1, asymptote, 1, 0, negative 1, asymptote. Okay, so the last thing is this. We're going to sketch the rest of the curve of tangent. It looks kind of like a cubic curve. It's going to come in, get a little bit more flat, and then it's going to follow the asymptotes all the way down. All right, hopefully you guys saw these curves last year, but let's just graph those. All right, one thing to keep in mind, you guys, the amplitude here was 1. That was the number in front of tangent. So that's what informs us of the 1s and the negative 1s. If I were to change that and write like 2 times the tangent of x, then these would go to 2 and negative 2. All right, so just keep that in mind there. But that's our tangent curve. All right, so let's try one more now. This is the tangent of 2x. So the period here is the standard period of tangent, which is pi, same for cotangent, divided by the frequency. So our period is pi over 2, which means that our sub-interval length is pi over 2 divided by 4. That's what we're counting by, or where the key points are going to lie. So that becomes pi over 8 in this case. So every tick mark along the x-axis is actually going to be a key point for this tangent curve. All right, remember, order of key points. Tangent always starts at 0, 1, asymptote. And then negative 1. Oops, that point wasn't on 1 there. 1, okay. -1, 0, 1. Asymptote. And then that pattern is going to repeat. I'm going to continue this pattern over and over and over again until I've got my graph full. So go ahead and do that. I'll be right back. All right, tons of tangent curves there. You guys are going to take this and apply this to cotangent. So think about cotangent in terms of x over y. Figure out where cotangent is undefined, where it's 0, where it's 1, and where it's -1. And do the same thing. Graph the asymptotes and then plot those points and sketch the rest of the curve. I will be focusing when I'm looking at your homework and grading this particular assignment more carefully at those cotangent curves. So once you've sketched the cotangent curves on the last page of this handout on page 35, please check using a graphing calculator or Desmos to make sure you've got those graphs and those curves just right before you scan and turn the homework in. The last thing is this. I would highly recommend that you think about what the graphs of the negative tan x look like and what the graphs of negative cotan x look like as well. How are they different from each other? And could you possibly represent the equation of tangent in terms of cotangent and vice versa? So be really familiar with those as well. The handout's not going to get into those, but I'm not assigning bookwork that will. So just be familiar with those before you guys get to the test next week.